Bom, rapaziada, vamos continuar. O que eu não tô entendendo é o seguinte. Ah, tá. Eu tô tentando regular a câmera aqui, calma aí. Aí, será que assim fica melhor? Não sei. Pô, mas aqui fica muito pra lá. Não sei que eu vire. Não, mas aqui. Mano, vai ser assim. Pronto, claridade. Quero só ajeitar. Ah, era aqui, era nessa posição aqui. Achei, achei, achei. Só ajeitar o fio aqui. Caraca, mano. Foda, foda, tá foda. Pô, foda que não tem como eu baixar mais a câmera. Fazendo uma gambiarra do caraca. Ah, acho que aqui tá bom. Acho que tá bom aqui. É bom, vamos lá. Soltar o play aqui, né? Vambora. Vamos lá, eu vou começar fazendo alguns exercícios sobre máscara de rede. Eu vou pedir pro GPT gerar aqui pra mim. Gere. Vou botar 10. 10 exercícios sobre, sobre máscara de rede e subrede. Com o intuito de fixação.
another lesson from my new course on networking fundamentals. The first module. There are far too many. Hello, welcome to the first lesson in the first module. Hello, welcome to another lesson from my new course on networking fundamentals. The first module of this course will teach you everything you need to understand how data flows through the internet. In this lesson, we'll be taking a look at the internet from the host's perspective, and we're going to look at everything a host does to speak on the internet. Before watching this video, it is recommended to have watched the prior lessons in this module. In lesson 1, we unpacked the concepts of a host, IP address, network, switches, and routers. And in lesson 2, we took a practical look at the OSI model and showed you how each layer contributes to the overall goal of networking, which is moving data between hosts. There will be links to each of these lessons in the description. In this lesson, we're going to illustrate everything hosts do to speak on the internet, and we're going to do this across 2 scenarios. The first scenario will outline everything that occurs for 2 hosts which are directly connected to one another to communicate. And the second scenario will outline everything that occurs for 2 hosts to communicate on opposite sides of a router. Now regarding this first scenario, hosts don't actually know what they are connected to. So whether host A is directly connected to host B, or whether there is one switch or multiple switches in between, either way, host A is going to follow the same steps. So this first scenario is actually showing you everything that hosts do when communicating with other hosts on the same network, regardless of how they are connected. And regarding that second scenario, hosts also don't know whether what they are trying to speak to is on the other side of one router, or multiple routers, or on opposite sides of the internet. So again, we'll remove all the extra variables to keep it simple, which will tell us exactly what a host does to speak to any other host on a foreign network. These 2 scenarios will illustrate 100% of the communication that occurs on the internet from the perspective of each host. Now we're going to be doing this in 2 parts. In part 1, in this video, we'll show you all the steps hosts take to communicate to other hosts on the same network. And in part 2, in the next video, we'll show you how it changes if you add a router to the mix. That being said, let's jump right into it with our first illustration. So here we have 2 hosts. And these 2 hosts are directly connected to each other. Now they don't know that, so what they're going to be doing is identical if there were hubs or switches in the mix. Now both of these hosts have a NIC, which this wire is physically connected to, which means both of these hosts have a MAC address. I'm providing only the first 4 digits of each host's MAC address to conserve screen real estate. Moreover, both of these hosts have IP addresses and subnet masks. We defined earlier in this module that IP address serves as the identity of each host. We didn't yet give you a definition for a subnet mask, but a subnet mask essentially tells you the size of a particular network. Now, this is all done through a process known as subnetting, and we're not going to be covering subnetting in this module. If you're interested in learning subnetting, go and check out the free videos we've created at subnetipv4.com. Host A has some data it needs to send to host B. Now from the network perspective, we don't know or care what that data is. It's just a bunch of 1s and 0s that needs to go from host A to host B. Host A also knows the IP address that it's trying to speak to. It knows the IP address of host B. Now how it knows that is somewhat outside the scope of this video, but the simplest explanation is maybe the user of host A jumped on the command prompt and typed ping 1011.33. This provided the IP address to host A that needs to receive this data. Alternatively, maybe host A acquired the IP address of host B through DNS. DNS is a protocol which converts a domain name into an IP address. For example, when you jump on your web browser and type in practicalnetworking.net, DNS is what's going to turn this domain name into an IP address that your computer can send a web request to. One way or another, host A is going to use something like this in order to know the IP address that it's trying to send the data to. Moreover, host A also knows that the IP address that it's trying to speak to is on host A's own IP network. Host A will do this by looking at its own IP address and comparing it to its own subnet mask to determine how many other IP addresses are on the same network. Now all this again is done through subnetting, which we won't be covering in this module. For now, just take my word for it that host A knows that 10.133 is on the same IP network of host A. If you want to learn more about subnetting, however, feel free to check out the free videos at subnetipv4.com. Either way, since host A knows the IP address of who it's trying to speak to, it's able to create the layer 3 header to attach to this data. This layer 3 header is going to serve the function of end-to-end delivery. Therefore, it's going to include a source IP address of whoever is sending the data, in this case host A, and a destination IP address of whoever is meant to receive the data. Now, of course, layer 3 cannot interact with a wire. For that, we need layer 2. So host A next needs to add a layer 2 header to this packet. The problem is that host A does not know host B's MAC address. If we look back at our example of how host A knew host B's IP address, many of you have used the ping command, and I imagine all of you have typed in ping and then an IP address. But notice you never typed in ping, an IP address, and a MAC address. You only provided the IP address to the computer. The computer figured out the MAC address on its own, and that's exactly what host A is going to have to do. Host A is going to have to use the address resolution protocol, or ARP, to resolve host B's MAC address. This, in fact, is exactly the purpose of ARP. ARP is meant to link a layer 3 address to a particular layer 2 address. So let me show you how that works. Host A needs to use ARP to resolve the target IP address's MAC address, meaning that MAC address right there. What it's going to do is shoot out an ARP request. This ARP request is going to ask for the MAC address which is associated with a particular target IP address. In this case, the IP address we are trying to resolve, 10.1.1.33. Moreover, this ARP request is going to include the sender's MAC address. Host A is going to include its own IP address and MAC address in the request itself. This will be useful so that host B can respond directly to host A later on. Now notice that the ARP request included a layer 2 header. This layer 2 header is meant to take the ARP payload and get it delivered to host B. But that layer 2 header does not have a destination MAC address of B's MAC address. If host A knew host B's MAC address, it wouldn't have to do ARP to begin with and could just populate the MAC address in this layer 2 header from the very beginning. Instead, this layer 2 header is sent as a broadcast, meaning it's sent to everybody on the network. What that means is that it has a destination MAC address of all Fs. The all Fs MAC address is a specially reserved MAC address which is meant to be used whenever you want to deliver a packet to everybody on the local network. That is by definition a broadcast. Now, if you're interested in learning more about broadcast, I created another video which discusses local broadcasts and directed broadcasts. There'll be a link for that video in the description. As for us, we're going to continue. ARP mappings are stored in what's called an ARP cache. Every device which has an IP address has an ARP cache. Host A has an IP address and host B has an IP address. Therefore, they both have ARP caches. At the moment, host A's ARP cache simply states that we're trying to resolve the 10.1.1.33 IP address to a particular MAC address. Host B's ARP cache is currently empty. When this request, however, makes it across the wire, you'll see something happens to host B's ARP cache. Notice, host B was able to populate an entry in its ARP cache for host A. It was able to identify that the IP address 10.1.1.22 maps to the MAC address A2A2. That occurred because in the original ARP request, host A provided its own MAC address. So by simply receiving an ARP request, host B was able to learn an ARP entry. Host B will now respond to that ARP request by sending what's known as an ARP response. That ARP response will include the mapping that host A was trying to resolve, specifically the IP address 10.1.1.33 and the MAC address that owns it. This ARP response is sent unicast, meaning directly back to host A. Since host B knows host A's MAC address, it can create the layer 2 header, which will take the ARP response directly to host A and not have to interrupt everybody on the wire by using a broadcast. Either way, when that ARP response arrives on host A is able to create the ARP mapping that was listed in the ARP response. Now, host A has everything it needs to complete the layer 2 header for the data it was initially trying to send to host B. The layer 2 header is going to include a source MAC address of host A's MAC address and a destination MAC address of host B's MAC address. This layer 2 header will accomplish the goal of hop-to-hop delivery, which finally lets this data be sent to host B. Upon arriving to host B will discard the layer 2 header. Again, the whole purpose of that header was to get the packet from this NIC to this NIC. It did so successfully and can now happily retire in header heaven. Next, host B will discard the layer 3 header. Again, the only purpose of that header was to get this data from host A to host B, and it did that successfully and can therefore also retire in header heaven. And finally, the application on host B can process the data that it just received. So that is what is required to get some data from host A to host B. Now, presumably, host B is going to have a response, meaning it's going to have some ones and zeros it's going to have to send to host A. But the good news is host B
Então lembra, tá na mesma LAN, o computador, o 92.168.103, quer falar com o 92.168.101, ele vai olhar aqui, cara. Desculpa, 103 quer falar com o 102, né? Ele vai olhar o 92.168.102, ele sabe a máscara de subrede que ele tem, ele sabe que os dois estão na mesma subrede, então ele vai mandar um ARP request direto, perguntando por esse IP. Ele vai falar, cara, esse IP aqui, ó, 192.168.1.2, qual é o MAC dele? Vai mandar em broadcast, aí todo mundo vai receber. Ou 92.168, desculpa, 92.168.102 vai pegar isso aqui e vai falar, opa, ele está perguntando o meu MAC, porque está aqui o meu IP, né, 92.168.102. Aí ele vai responder em unicast para o 92.168.103, que o MAC dele é o 4F5BA364AB F1, beleza? Então, quando o cara está na mesma LAN, se comunica direto. Quando os caras estão passando por uma WAN, ou então eles estão em LANs ou VLANs diferentes, eles estão em subredes diferentes, né? Então esse cara aqui, por exemplo, o 92.168.103 quer falar na internet com o 200.200.102, beleza? Ele vai olhar, 200.200.102 está dentro da minha subrede? Não está, né? Porque os IPs desse cara aqui, ó, por exemplo, é um /24. Ele vai de um 92.168.101 até um 92.168.100.254. Se não for um IP desse, ele está fora. Então ele sabe que ele tem que mandar esse pacote para o gateway dele. Então ele vai fazer um ARP para o gateway. Cara, na prática, raramente você vai pegar um ARP para o gateway, porque ele faz isso de cara, tá? Então ele já vai ter o gateway lá na tabela de endereço MAC dele, ele já vai fazer de cara, o Windows não é tão burro assim, então o gateway já vai estar lá na tabela ARP dele, né? Registrado o IP com o MAC, tá? Mas se fosse a primeira vez, ele ia fazer isso, ele ia consultar aqui, ó, fazer uma consulta via ARP request, o gateway vai responder com um ARP reply. E aí, na hora dele montar o pacote IP, ele vai colocar como origem o IP dele, como destino o IP remoto, MAC de origem o MAC dele, né? Esse MAC aqui, ó. E o MAC de destino não pode ser o MAC dessa máquina, porque ele não está na mesma LAN. Alguém tem que encaminhar até lá, ele vai ter que chegar até lá, tem que mandar para um roteador, né? Então o MAC de destino vai ser o MAC do gateway, beleza? Vai ser o MAC do gateway. Joia? Por isso que ao invés de tentar resolver no ARP esse IP, ele tentou esse IP. Tentou do gateway. Cara, no IPv6...
Olá pessoal, bem-vindos a mais um vídeo aqui do canal e agora nós vamos falar sobre um protocolo que é desconhecido do grande público, mas que é muito importante que a gente conheça e entenda esse protocolo quando estamos estudando conceitos relacionados às redes de computadores e à própria internet. É o protocolo ARP, o ARP, o Address Resolution Protocol. Isto quer dizer em português, o protocolo de resolução de endereços. E qual é a grande função, pessoal, desse protocolo ARP? Bem, dentro de uma rede local, muitas vezes é necessário a associação entre os endereços físicos das máquinas, dos dispositivos, e também com o próprio endereço IP, que é o endereço lógico. Observa uma associação entre os endereços físicos das máquinas que compõem a rede e seus endereços IPs. Isso porque quando a gente usa um computador para acessar uma rede, nós temos, por exemplo, a placa de rede. E a placa de rede, que é um hardware, ela tem um endereço físico, que é o chamado endereço MAC. Mas quando essa mesma máquina, esse mesmo computador está acessando, por exemplo, a internet, ele também usa um outro endereço, que é um endereço lógico, que é o chamado endereço IP. Então nós temos o endereço físico dos dispositivos de rede, que é o endereço MAC, e temos o endereço lógico, que nos conecta à internet, que é o endereço IP. E para fazer uma associação entre esse endereço físico e o endereço lógico é que existe o protocolo ARP. Então, no protocolo ARP, os endereços IPs, que são os endereços lógicos, são mapeados em endereços MAC, que são os endereços físicos. Essa é a grande função do protocolo ARP. Simples assim. Então, se você entrar numa questão de prova, de concurso, saiba que se a prova perguntar, a grande finalidade do protocolo ARP é simplesmente essa. É conseguir fazer uma associação do endereço físico com o endereço lógico. Pegar os endereços IPs, que é o endereço lógico, eles acabam sendo mapeados em endereços MAC, que são os endereços físicos dos dispositivos de rede, como por exemplo, a placa de rede que você usa tem um endereço físico e esse endereço é o endereço MAC. Mas quando você está acessando a internet, você está usando o endereço lógico, que é o endereço IP. Por isso que é necessário fazer essa
has all the necessary information in order to respond much quicker than it initially took. Host B knows who it's trying to communicate, so it's able to create the layer 3 header with a source IP address of host B and a destination IP address of host A. And since host B's ARP cache is already populated, it's able to create a layer 2 header that includes its own MAC address as the source and host A's MAC address as the destination, which it knows because it's stored in its ARP cache. In fact, any further data exchange between these two hosts now happens very easily, because both hosts have everything they need in order to create the layer 3 and layer 2 headers successfully. And that wraps up our lesson on everything hosts do to speak to another host, everything they need in order to create the layer 3 and layer 2 headers successfully. And that wraps up our lesson on everything hosts do to speak to another host on the same network. The key takeaways of this lesson is understanding all the steps a host takes when speaking to another host on the same network, understanding that those steps are the same regardless on whether there are switches or hubs in between the two hosts, and finally, understanding ARP and how it works and how it links a layer 3 address to a layer 2 address. In the next video, we're going to add a router between these two hosts to show you how these steps change. This will illustrate everything a host does to speak to another host on a foreign network. But that wraps up this video. I hope you enjoyed this video. I want to thank you for watching, and I'll see you in the next video as we unpack how hosts communicate through a router. Hey you! YouTube, I hope you enjoyed that free lesson for my new course on networking fundamentals. I'll be releasing the entire first module for free here on YouTube. I want this course to be the ultimate networking. Hello. Welcome to another lesson from my course on networking fundamentals. The first module of this course will teach you everything you need to understand how data flows through the internet. In this video, we're going to continue our lesson discussing everything hosts do to send data on the internet. Also, you should the series. This lesson uses this video. It is recommended to have watched lesson 1 and lesson 2 from the series. This lesson uses and elaborates on many of the concepts introduced from prior lessons. Also, you should have already watched part 1 of this lesson. This video is a direct continuation. In part 1 of this lesson, we illustrated everything hosts do to communicate to other hosts on the same network. In this video, we're going to add a router, and we're going to show you everything a host does when trying to communicate with another host on a foreign network. We're going to use this topology to show you everything host A does to send data to host C. Both of our hosts and our router has a MAC address and IP addresses. And once again, I'm only showing you the short version of the MAC address to conserve screen real estate. Now this /24 you see on all of them is simply another way of representing this subnet mask. And again, the subnet mask simply defines how big a particular network is. All of this is a function of subnetting, and once again we are not going to be covering subnetting in this module. In the first part of this lesson, we mentioned that anything with an IP address has an ARP cache. Well, host A, the router, and host C all have an IP addresses, so all three of them have an ARP cache. But this video, we're going to be focusing on host A, so we're only going to show you host A's ARP cache. And we're going to show you its functionality, as host A has some data to send to host C. Now, host A already knows host C's IP address. We mentioned some reasons for this in the last video, but essentially, that IP address could have been provided by the user or provided by the application that is creating this data that is meant to be sent to host C. One way or another, host A already knows the IP address it's trying to speak to. But in particular, host A knows that that IP address is on a foreign network. It's going to know this by looking at its own IP address and subnet mask and comparing it with a target IP address. That's how it's going to know this IP address is on a foreign network. Now once again, all of that is done through the magic of subnetting, and if you're interested in knowing how that works, check out the videos at subnetipv4.com. But insofar as this video, go ahead and take my word for it that host C's IP address is indeed on a different network than host A's IP address. Either way, since host A knows the IP address it's trying to speak to, host A is able to create a layer 3 header identifying the two endpoints of this communication. That layer 3 header is going to have a source IP address of host A and a destination IP address of host C. Next, host A needs to create a layer 2 header. The purpose of the layer 2 header is going to be to take the packet from hop to hop. In this case, since the target we are trying to speak to is on a foreign network, our next hop is going to be the router. Meaning, the purpose of this layer 2 header is going to be to get this packet to the router. The problem is at this point in time, since host A's ARP cache is empty, host A is unable to complete the layer 2 header that'll take this packet to the router. Host A, just like before, is going to have to use ARP to resolve the router. Host A, just like before, is going to have to use ARP to resolve the router. Host A, just like before, is going to have to use ARP to resolve the MAC address of the router. But there's something we have to mention. How does host A even know the router's IP address? Well, the answer to that is that the router's IP address is already configured on host A as host A's default gateway. When you connect a computer to the internet, there are three things that you have to configure. An IP address, a subnet mask, and a default gateway. On a Windows computer, if you type ipconfig into the command prompt, you'll see all three of these things listed. Here, I'm showing you exactly what it might look like on host A itself. Notice the IP address matches host A's IP address, the mask is a /24 mask, and in particular the default gateway is highlighting the IP address of our router. That's how host A knows the router's IP address, because it's been configured as its default gateway. That's the IP address that host A is going to have to resolve with ARP. So just like we mentioned in the last lesson, host A is going to shoot out an ARP request. That ARP request is going to ask for the MAC address that correlates to a particular IP address. And again, host A is going to include its own ARP mapping in the request itself. That ARP request is going to get to the router, and then the router is going to generate a response. That response is going to include the mapping that host A was interested in learning. The IP address 10.1.1.1 maps to the MAC address E5E5. And when that ARP response arrives on host A is able to populate its ARP cache with the mapping for its default gateway. It can then use this mapping to complete the layer 2 header. The destination MAC address for that layer 2 header is going to be the router's MAC address. This will allow this header to handle hop-to-hop delivery of this packet. And now that data can finally be sent across the wire, where it will be received by the router. Upon receiving this, the router is going to discard the layer 2 header. The whole purpose of that header was to get this packet from host A's NIC to the router's NIC. That header did that successfully and can go and retire happily in header heaven. And at this point, the router is going to take over. Presumably, the router is going to add layer 2 headers as necessary to get the packet across the next hop, whether that hop is directly to host C or whether that hop is across multiple routers on the internet. One way or another, from host A's perspective, the job is done. It did everything it needed to do to get the data to the router, and from here, we're just going to hope that the router can do the rest of the work to get it all the way to host C. Now, I want to highlight something important for you. This ARP entry that host A resolved in order to get the packet to the router can be reused to speak to any host in foreign networks. So let me show you what I mean by that. So here again is the layer 3 and layer 2 header that were used to get this data to host C. And let's go ahead and add other hosts to our topology. Let's say now host A is going to be trying to speak to host D. Well, since this is a new endpoint, we're going to need a new layer 3 header. This layer 3 header is going to have a source IP address of host A, as before, and of course a destination IP address of host D. But notice the layer 2 header doesn't change. Host A's first hop is always going to be to the first router, and therefore the source MAC address and destination MAC address are always going to identify those two NICs. So this ARP process that we had to go through to resolve the router's IP address really only needs to happen once. Once host A knows the router's MAC address, it can reuse that MAC address to speak to any host in a foreign network. In all cases, the layer 2 header is going to look the same. So it's important to understand this ARP process is very crucial to how data moves through a network. It's actually the first step that host A or any host takes when it's trying to send data on a network, is to determine if the target IP it's trying to speak to is on my own network, the local network, or a foreign network. If it's on a foreign network, like we just showed you, ARP is going to try and resolve the default gateway's IP address. And if it's trying to speak to something on the local network, ARP is going to try and resolve the target IP address directly. That's actually the illustration we showed you in part 1 of this lesson. We showed you that for host A to speak to host B, the ARP entry that host A had to create was for host B's IP address directly. This is what allowed host A to create this layer 2 and layer 3 header to get data from host A to host B. And that wraps up our lesson on everything hosts do to speak on the internet. The key points of this lesson was understand
esse processo de eu tava falando sendo mutada. do processo do computador A mandar para, tipo, computadores que estão fora, estão na internet, não estão na mesma rede, é meio que a camada 2, né? A camada dela já fica pronta, porque é sempre a mesma. Sempre vai partir, por exemplo, do meu computador pro meu modem, do meu computador pro meu modem. E isso é fixo, que foda. O dado é montado. Até chegar no MAC address que tem o IP de destino. Foda. Vamos ver como é que funciona os switches agora.
Hello, welcome to Lesson 4 of Module 1 of my new course on Networking Fundamentals. In this lesson, we're going to be picking apart switches, and we're going to show you everything a switch does to facilitate communication. As we discussed in the first lesson, switching is the process of moving data within networks. And a
Switch é o processo tipo de uma mesma rede. Não inclui redes distintas, né? Switch ele é utilizado para conectar hosts distintos e fazer a transferência de dados na mesma rede. Na mesma rede, isso. E já roteador é chamado processo de transferência de dados em roteador é chamado routing, que é entre roteadores. É o processo de transferência de dados entre os roteadores, ou seja, entre redes diferentes.
switch is simply a device whose primary purpose is switching. We're about to show you an illustration of a switch and everything it does to funnel communication between these hosts. But it's important to understand
Cara, eu tenho que ficar olhando pra legenda, senão não dá.
anything that claims to do switching is going to operate the way we describe a switch to operate. We are simply going to be describing the rules of switching. For these hosts to communicate with one another, they each need IP addresses and MAC addresses. Now, since a switch only facilitates communication within a network, this tells us that all of these devices that are speaking through the switch must belong to the same IP network. In this case, that IP network is the 10.1.1.x network. In this lesson, we're going to illustrate everything that the switch does to enable communication between host A and host D.
Ele permite a comunicação entre...
Now, in the last lesson, we described the host role in all this. We described that the host is going to generate some data to send to host D, and then add a layer 3 header to that data, which includes the source of host A and a destination of host D's IP address, Then host A is going to perform ARP to figure out the MAC address which correlates to that
Gera
destination.
broadcast, qual é o MAC address do computador D. Opa, é meu. D4, joga o unicast pro switch joga para quem deve jogar.
IP address. Then host A is going to add a layer 2 header, which indicates host A's MAC address and host D's MAC address. All of that we described in the last lesson, and all of that still applies. In this lesson, we're just going to be focusing on the switch. And if you recall, a switch is a layer 2 device, which means
Camada 2, né? Isso. E camada 3 é o quê? É o roteador, né? Isso, né? Isso. Isso, né? É.
they're only going to be using the layer 2 header to
Eles apenas usam a camada 2 para tomar decisões.
make their decisions, which means the switch doesn't look at the layer 3 header at all. In fact, everything after the layer 2 header, from the perspective of the switch, is simply considered data. You and I know there's a layer 3 header in here, but from the switch's perspective, it doesn't care about that layer 3 header, it's just going to make...
Ah, ele não precisa saber sobre a camada 3 porque ele só usa os dados, os cabeçalhos do dado da camada 2, né?
decision based upon the layer 2 header. In fact, we can actually get rid of anything IP related on this topology, because if all we're doing is focusing on the switch, we don't actually need to consider the IP addresses that are communicating. We're going to show you everything that happens to get this data to host D through this switch. Now, I want to point out that we are starting from the position that host A already knows the MAC address it's trying to speak to. Normally, host A would have to discover this using ARP, but for our illustration, we're going to assume host A already knows the MAC address it's trying to speak to, so we can leave ARP out of this illustration entirely. With that said, let's go ahead and explain how switches facilitate communication within networks. Switches use and maintain a MAC address table. A MAC address table is a mapping of switch ports to MAC addresses. Each of the hosts in our topology are plugged into this switch in a particular port. For instance, host C is plugged into port 6. Now every different switch out there uses different numbering schemes for their ports. For the sake of illustrations, I'm just going to use these numbers 5, 6, 7, and 8. A MAC address table then is going to include the mapping of a particular switch port and the device that's connected to that port, meaning it's going to know that out port 7 exists a device with the MAC address B2B2. Now this MAC address table doesn't start out populated. In fact, it starts out empty. And as data is flowing through this topology, the switch will populate this MAC address table. Beyond this MAC address table, the switch is only ever going to perform 3 actions: learning, flooding, and forwarding.
O que é flood e flood? Acho que flood não é prêmio, sei lá, mas tem que ver o que se encaixa ali, né? Flood. Enchente. Forward. Avançar. Tá, vamos entender o conceito de cada um.
If you understand these 3 actions, then you'll understand how switching works.
Tá, se você entender essas 3 ações, você entende como o switch funciona.
Every switch you come across, regardless of the platform, regardless of the vendor, regardless of the code version, is only going to do 3 actions. These are actually the rules of switching in general.
É uma regra do switch.
So let me show you how they work. So host A is going to start by putting this information on the wire. That will arrive on the switch on port 5. And this is going to allow the switch to perform its first action, which is to learn. The learning action has the switch update its MAC address table with a mapping of the switch port and the source MAC address of the received frame. Meaning, on port 5, this switch just received a frame with a source MAC address of A1A1, which allows the switch to update its MAC address table, indicating that the device on port 5 owns the MAC address A1A1. That is the learning action, and the switch is going to try to learn the source MAC address for every frame that the switch receives. Now the switch has to figure out what it's going to do with this frame. It's going to look at the destination address of that frame to determine that this is meant to be delivered to the device which has the MAC address D4D4. Now you and I know that that device exists over here, but this MAC address table lists everything that the switch knows. So at this point in time, the switch does not know what port the MAC address. Now the switch has to figure out what it's going to do with this frame. It's going to look at the destination address of that frame to determine that this is meant to receive. Now the switch has to figure out what it's going to do with this frame. It's going to look at the destination address of that frame to determine that this is meant to be delivered to the device which has the MAC address D4D4. Now you and I know that that device exists over here, but this MAC address table lists everything that the switch knows. So at this point in time, the switch does not know what port the MAC address D4D4 exists on, which means the switch's only option is to duplicate that frame and send it out all ports. This is the only way the switch can ensure that whatever owns that MAC address does get this frame. Now notice that the switch did not forward the frame back out port 5. When it duplicates the frame and sends it out all ports, it's going to send it out all ports except the port that received the frame initially. The idea there is that if this frame arrived on port 5, there's a good chance that the destination does not exist back out port 5. So that is the flooding action. And all other hosts in this network are going to...
Tá. Então, learn é quando eu envio o dado e aí ele, opa, essa porta aqui é essa, hein? Float é quando eu tô querendo enviar o dado para um computador, sei lá, para um computador D, que está na mesma rede do que eu, sendo que o switch acabou de ser colocado. Ele não sabe, ele conectei, mas ele não sabe que o MAC address do computador D é tal. Então, ele vai pegar o dado que eu enviei e vai enviar uma requisição para todo mundo. E aí, provavelmente, o computador que receber vai ter que retornar. Opa, sou eu aqui, hein? E aí, ele vai aprender que, sei lá, por exemplo, a porta 8 é o computador D4D4. Vamos ver se é isso?
Receive a copy of this frame. Now when host B and host C receive this frame, they're going to look at the destination MAC address to determine that they are not the intended recipient for that frame. They are therefore simply going to silently discard that frame. Host.
Tá, quem não for, tipo assim, se eu enviei pro computador D e o computador E, C e B receberam, eles só vão descartar, porque eles, opa, esse MAC address aqui não é o meu, e eles jogam fora.
D, however, will be looking at the destination MAC address to realize it is destined to host D, and host D will accept that frame for processing. And that is how data will get from host A to host D. Now, inevitably, host D is going to generate a response to send back to host A. This response is going to have a source MAC address of host D's MAC address and a destination MAC address of host A's MAC address. Host D is going to put this response on the wire, where it'll arrive on the switch on port 8. This will allow the switch to once again perform its learning action. It's going to update its MAC address table, indicating that something just arrived on port 8 with a source MAC address of D4D4. This allows the switch to create this mapping. Now, the switch is going to try and figure out what it's going to do with this frame. And once again, it's going to look at the destination MAC address A1A1 to determine where to send this frame next. The difference, however, is that now the switch knows how to deliver a frame to A1A1. It knows that A1A1 exists out port 5. This will allow the switch to simply forward that frame out the appropriate switch port. That is the third action of the switch, the forwarding action.
Calma aí.
The forwarding action allows the switch to simply forward that frame out the appropriate switch port. That is the third action of the switch, the forwarding action. The forwarding action allows the switch to deliver a frame directly to the switch, the forwarding action. The forwarding action allows the switch to deliver a frame directly to the appropriate switch port because the destination MAC address exists in the MAC address table. This will allow the switch to send that frame directly to host A. And that is how the response data will go from host D to host A. Now, at this point, anything else that A and D need to send to each other will simply go directly to each other. Now that the MAC address table is populated with either of those hosts' MAC address, anything A and D send to each other is going to go directly to each other without having to do the flooding action, which means host C and host B will not get a copy of any of that data. And that wraps up our discussion of how switches work. Again, switches use and maintain a MAC address table, which is a mapping of a switch port to a MAC address, and switches perform only these three actions. And if you understand these three actions, you now understand how any switch for any vendor on any platform facilitates communication within a network. But before I let you go, there are two more ideas I want to leave you with. Our illustration involved host A sending a packet to another host. But everything we just showed you would still apply if this wasn't actually a host and it was instead a router and host A was trying to apply if this wasn't actually their host. But everything we just showed you would still apply if this wasn't actually a host and it was instead a router and host A was trying to send something to the router in order to speak to something else out on the internet. The only thing that would be different would be the layer 3 header. And as we discussed, the switch doesn't even look at the layer 3 header to do it. Would be the layer 3 header. And as we discussed, the switch doesn't even look at the layer 3 header to do its job. Which means this process is exactly the point anything else that A and D need to send to each A. Now, at this point, anything else from host, now the switch is going to try and figure out what it's going to do with this frame. And once again, it's going to look at the destination MAC address A1A1 to determine where to send this frame next. The difference, however, is that now the switch knows how to deliver a frame to A1A1. It knows that A1 directly to the appropriate switch position. The forwarding action allows the switch to deliver a frame directly to the appropriate switch port because the destination MAC address exists in the MAC address table. This will allow the switch to send that frame directly to host A. And that is how the response data will go from host D to host A. Now, at this point, anything else that A and D need to send to each other will simply go directly to each other. Now that the MAC address table is populated with either of those hosts' MAC address, anything A and D send to each other is going to go directly to each other without having to do the flooding action, which means host C and host B will not get a copy of any of that data. And that wraps up our discussion of how switches work. Again, switches use and maintain a MAC address table, which is a mapping of a switch port to a MAC address, and switches use and maintain a MAC address table for discussion of how switches work. Again, switches use and maintain a MAC address table, which is a mapping of a switch port to a MAC address, and switches perform only these three actions. And if you understand these three actions, you now understand how any switch for any vendor on any platform facilitates communication within a network. But before I let you go, there are two more ideas I want to leave you with. Our illustration involved host A sending a packet to another host. But everything we just showed you would still apply if this wasn't actually a host and it was instead a router and host A was trying to send something to the router in order to speak to something else out on the internet. The only thing that would be different would be the layer 3 header. And as we discussed, the switch doesn't even look at the layer 3 header to do its job. Which means this process. is exactly the same whether host A is speaking to a host on the local network or trying to send something to a router in order to speak to something on a foreign network. The second idea I want to leave you with is that we showed you how traffic flows through a switch. We illustrated host A sending something through the switch initially to host D. Understand that switches have MAC addresses. Again, any NIC has a MAC address. But you'll notice that this MAC address was completely uninvolved for any communication going through the switch. But what if you wanted to send something to the switch? Well, if you're trying to send something to the switch, then this MAC address would be involved. But not only would the switch need a MAC address, it would also need an IP address. And at this point, if you've configured an IP address on the switch and you're trying to send traffic to the switch is essentially acting as a host on the local network. It's going to follow all the rules that we described in the prior lessons that hosts follow in order to communicate on a network. The switch's MAC address and also its IP address will only be used if you're sending traffic to or receiving traffic from the switch. Perhaps you're trying to log into the switch using Telnet or SSH in order to manage the switch. But for any traffic going through the switch MAC address and IP address will be completely uninvolved in the process. The switch is merely going to perform these actions over here in order to facilitate communication within a network. And that wraps up part 1 of our lesson on switches. In the next lesson, we're going to unpack 3 more ideas. We're going to describe unicast flooding and explain how that's different from a broadcast. We're going to briefly define VLANs and show you how these actions are different or not if VLANs are being used. And finally, we're going to show you how communication flows through multiple switches, showing you how these actions are still the same regardless of how many switches data is flowing through. Hello, welcome to another lesson from the first module of my new course on networking fundamentals. This first module will teach you everything you need to understand how data flows through a network. In this lesson, we're going to continue our discussion of switches, and we're going to unpack everything switches do to facilitate communication within a network. In the first part of this lesson, we discussed MAC address tables and how they work, and the 3 actions a switch will take. If you haven't seen that video, go ahead and pause this video right here and watch that video first. This video is a direct continuation. In this video, we're going to introduce 3 more ideas. We're going to discuss unicast flooding and broadcast. We're then going to discuss VLANs, and finally, we're going to show you how these actions apply when multiple switches are involved. That said, let's get right into it. In the last video, we showed you how host A sent this frame to host D. We showed you that when host A put that frame on the wire, it arrived on port 5, which allowed the switch to learn this entry in its MAC address table, and then the switch had to flood this frame because it didn't know where the MAC address D4D4 existed. Now this frame was a unicast frame. The definition of unicast is a one-to-one communication, and you can tell this is a unicast frame because the destination MAC is another host. But what if instead host A had sent a broadcast? For instance, what if instead host A had sent an ARP request? Now we told you an ARP request is a broadcast frame, meaning it has a destination MAC address of all Fs. This is a specially reserved MAC address which indicates that this content needs to be delivered to everybody on the local network. Well, if this frame was the first frame that host A had sent, the learning process would have been identical, because either way, the switch will have received something on port 5 with the source MAC address of A181. So this MAC address entry would have been the same. But since this is a broadcast frame, the switch wouldn't even look at its MAC address table in order to forward this frame. A broadcast frame is always going to be flooded by a switch. Unicast frames, however, are only sometimes flooded, specifically if the destination MAC address is not in the MAC address table. If, at the time of this frame arriving, the switch had known the location of the MAC address D4D4, then this frame would simply be forwarded directly out to host D. The difference I'm trying to point out is the terms unicast and broadcast have to do with a type of frame, and both of those are different from the term flood. Flood is simply an action that a switch will take, whereas a broadcast is an actual type of frame, specifically a frame with a destination MAC address all Fs. A switch will only do these 3 actions. A switch will never broadcast anything. The only time a switch is going to send a broadcast is if traffic is going to or from the switch. But at that point, the switch is essentially acting as another host. So insofar as traffic going through the switch, a switch will never broadcast anything. A switch will only perform these 3 actions. So that is how unicast flooding is different from a broadcast. Again, a broadcast is always flooded, whereas unicast frames are occasionally flooded. So that wraps up our discussion on broadcast versus flooding, which brings us to VLANs. VLANs stand for Virtual Local Area Networks. In this section, we're going to briefly define VLANs, but only as much as needed as to discuss these switch actions. What VLANs allow you to do is they allow you to take a switch and divide the switch ports into isolated, independent groups. I can group these ports into one isolated groups called VLAN 20, and these ports into another isolated groups called VLAN 30. Now, this switch essentially acts as multiple mini switches. And each of these mini switches are going to perform each of these actions independent from the other. Meaning the switch is going to maintain one MAC address table for VLAN 20 and another MAC address table for VLAN 30, and the switch will do all three of these actions confined to these isolated independent groups. That is what VLANs do, is they essentially allow you to create mini switches within the big physical switch. So you can see that these actions still apply if you're using VLANs. All you're doing is confining these actions to a specific set of ports. Now that is as far as we want to go in this lesson regarding VLANs. If you want to learn more about VLANs, I've created a video which discusses VLANs in more detail. There'll be a link in the description, and I'll also add a YouTube card right there. Furthermore, if you want to access all the content I've ever produced regarding VLANs, simply type pracnet.net/VLANs into your web browser, and you'll be taken to an index with links to everything I've ever produced about VLANs. Otherwise, we're going to continue in this lesson and discuss how switches operate when there are multiple switches involved. To illustrate this, we're going to use this topology right here. I'm going to show you how everything we discussed insofar as switches still applies if multiple switches are involved. Now, both of these switches are going to maintain their own independent MAC address table. They're not going to share information with each other insofar as what MAC addresses they know. They're simply both going to perform these three actions and populate their own independent MAC address table. And I'm going to show you how that works by showing you everything that occurs for a frame to go from host A to host B. Now once again, this is a unicast frame. It has a destination MAC address of another host. So this illustration is going to start with the assumption that host A knows the MAC address it's trying to speak to, meaning we're going to leave ARP out of this. That said, when host A sends this frame out onto the wire, it'll arrive on the blue switch on port 1, which will allow the blue switch to learn a MAC address entry for port 1. Then the blue switch is going to look at the destination MAC address of that frame and realize it does not know currently where the host B exists. Therefore, it's simply going to flood that frame all other ports. The blue switch just did unicast flooding. Either way, host C will get a copy of this frame and will silently discard this frame since it is not the intended recipient. And now we can continue this process from the green switch's perspective. From the green switch's perspective, something just arrived on port 4 with a source MAC address of all A's. This allows the green switch to learn a MAC address table entry for port 4. Then the switch is going to look at the destination, and again, the green switch doesn't currently know where the all B's MAC address is, so the green switch is then going to perform the flood action and send this frame out all ports. Once again, the green switch will flood the unicast frame. Host D will get a copy of this frame and will silently discard it. Host B will get a copy of this frame, accept it for processing, and theoretically generate a response. This response will be sent from host B's MAC address to host A. When this response arrives on the green switch will be able to learn the MAC address which exists on port 6, which is all B's. Then the green switch is going to look at the destination MAC address and realize that it does know how to deliver this frame, and it's going to send this out port 4. That would be the forwarding action. The blue switch will then have just received something on port 3 with a source MAC address of all B's. This allows the blue switch to learn the switch port to MAC address mapping for port 3. Then the switch is going to look at the MAC address table to determine that this frame should be sent out port 1, where it'll forward this frame out port 1, where it'll arrive on host A. So that's what needs to happen for data to get from host A to host B and back. And you'll notice all we did was simply use the information we discussed in the first video of this lesson and showed you how it applied to multiple switches. Now it's your turn. I want you to continue this illustration and map out the sequence of events for a frame to go from host C to host B and the response, and also from host C to host D and the response. If you do this, to pause, notice MAC address tables for both the blue and the green switches would look like this. Notice, in particular, that it is totally address mappings. Port 3 on this blue switch will have received traffic from host D and host B with a source MAC address of all Ds and all Bs respectively. So it's perfectly acceptable and expected for port 3 to have multiple mappings on the blue switch. If you're able to follow through this exercise, then you can say you definitely understand switching at this point. And in all cases, a switch is only performing these three actions and maintaining a MAC address table. That is again how any device that claims to do switching is going to operate. What we just illustrated are simply the rules of switching. And that wraps up Hello, welcome to Lesson 5 of Module 1 from my new course on Networking Fundamentals. This module will teach you everything you need to understand how data flows through the internet. In this lesson, we'll be picking apart routers, and we'll show you everything routers do to facilitate communication between networks. Before watching this lesson, it is recommended to have watched the prior lessons in this series. In Lesson 1, we discussed the concept of networks. We define them as a logical grouping of hosts. We mentioned that each network has its own IP address space, and each host has an IP address in that network's IP address space. We also defined switching. We mentioned that each network has its own IP address space, and each host has an IP address in that network's IP address space. We also defined switching as the process of moving data within networks, and then we grouping of hosts. We mentioned that each network has its own IP address space, and each host has an IP address in that network's IP address space. We also defined switching as the process of recommended to have watched the prior lessons in this series. In Lesson 1, we discussed the concept of networks. We define them as a logical grouping of hosts. We mentioned that each network has its own IP address space, and each host has an IP address in that network's IP address space. We also defined switching as the process of moving data within networks, and then we define routing as the process of moving data between networks. A router, which is going to be the focus of today's lesson, is simply a device whose primary purpose is routing. Then, in Lesson 2, we discussed a router, which is going to be the focus of today's lesson, is simply a device whose primary purpose is routing. Then, in Lesson 2, we discussed the OSI model. We used this illustration to discuss the interaction of Layer 2 and Layer 3. We showed you that for this host to send some data to this host, it would start by adding a Layer 3 header, which included a source and destination IP address of the two endpoints of the conversation. Then, a new Layer 2 header is added to facilitate each hop along the path between the two endpoints. All of this was discussed in detail in Lesson 2. Then, in Lesson 3, we focused on hosts, and we showed you everything hosts do when speaking to us. All of this was discussed in detail in Lesson 2. Then, in Lesson 3, we focused on hosts, and we showed you everything hosts do when speaking to other hosts. We first showed you everything hosts do to speak to other hosts in the same network, regardless of how they are connected. Then, we showed you everything hosts do to speak to other hosts in foreign networks, regardless of how they are connected. Both of these illustrations allowed us to discuss ARP, or the Address Resolution Protocol, and show you ARP's role in internet communication. All of this is the destination IP address of the two endpoints of the conversation. Then, a new Layer 2 header is added to facilitate each hop along the path between the two endpoints. All of this was discussed in detail in Lesson 2. Then, in Lesson 3, we focused on hosts, and we showed you everything hosts do when speaking to other hosts. We first showed you everything hosts do to speak to other hosts in the same network, regardless of how they are connected. Then, we showed you everything hosts do to speak to other hosts in foreign networks, regardless of how they are connected. Both of these illustrations allowed us to discuss ARP, or the Address Resolution Protocol, and show you ARP's role in internet communication. All of this is the prerequisite knowledge you'll need to fully understand this lesson. If any of these concepts are unfamiliar to you, please check out the first 3 lessons of this course. There are links in the description. In this lesson, we're going to be focusing on routers, and we're going to show you everything that routers do to move data across the internet. Here is a network with 2 hosts. Each of these hosts have a MAC address and is configured with an IP address in this network's IP address space. For these hosts to speak to each other, they would have to be connected to a switch, and this switch will facilitate all the communication within this network. But for these hosts to speak to
Pô, tô falando sozinho. E o switch ajuda a comunicação entre esses dois dispositivos. E o switch, ele vai para onde vai ser conectado a um roteador, né? Porque
a foreign network, we would have to add a router.
É isso aí mesmo.
Now routers are also connected to a network,
São conectados.
which means routers, just like hosts, also have an IP address and a MAC address, and all the rules of Layer 2 and Layer 3 that we've discussed prior still apply in order for these hosts to speak to this router. Now, in order to keep things simple and reduce the variables, since we've already talked about switches in the last lesson, we're going to leave switches out of this lesson entirely. But everything we discussed about how switches work still apply, so feel free to watch Lesson 4 if you want to understand how that works. In this lesson, we're just going to be focusing on routers. Now, if routers have an IP address and a MAC address, just like hosts, what then is the real difference between a router and a host? Well, my favorite definition for routers and hosts actually comes from the IPv6 RFC. If you're unfamiliar with RFCs, they stand for Request for Comments, and they are the type of document that define internet standards.
Tá, meio que tá falando que esse documento ele define as coisas, os conceitos da internet. Né?
In fact, if you're ever in a nerd argument with someone and you are debating about how something in the networking world works, whoever can quote the RFC always wins, because the RFC is literally the instructions that were used to build the internet. In any case, RFC 2460 is the IPv6 RFC, but it provides a useful definition for hosts and routers that also applies to IPv4. The RFC defines a node as anything which implements IP, or anything with an IP address. It then defines a router as any node that forwards packets not addressed to itself, which leaves the definition of a host to be a node that is simply not a router. So the real difference between a router and a host is that routers forward packets not destined to themselves. That is how they are different from hosts. For example, if this packet were to magically appear on this network and arrive on host D would take a look at the destination IP address and realize that it is not itself and would simply drop this packet. But if this packet were to arrive on router 1 would recognize that it is not destined to itself, but would still try and deliver this packet to the appropriate destination. That is how hosts and routers are different. Now,
Tá, meio que a principal diferença entre roteador e host é que o roteador ele vai tentar mandar esse pacote de dados, por exemplo, se não for ninguém da rede, esse roteador ele vai tentar enviar esse dado para o lugar certo, para o lugar de destino. Já um host não. Pô, isso aqui não é meu? Então já corta.
of course, for router 1 to actually forward packets not
Vamos ver se é isso. Diferença entre host e router. Host. Routers. Sim, né? Ah, tá. Então, roteador define o caminho, route envia o receptor.
into itself, there has to be another network that exists. So let's go ahead and add another network to our topology. A moment ago, we said that routers have an IP address and a MAC address. That, in fact, is what is meant by router 1 being connected to a particular network. But now that we have another network, router 1 is going to need another IP address and MAC address in order to be connected to the new network. Here, we've configured router 1 with the IP address 10.055.1, and that is what officially connects router 1 to this new network. In order to accomplish this goal, routers must maintain a map of all networks that they know about. This map is known as the routing table. Inside a routing table is what's known as routes, and each route is merely a set of instructions for how to reach a specific network. For our topology over here, there are two networks, 10.055 and 10.044. And router 1 is going to have a route correlating to each of those networks. The first route will tell router 1 that to reach anything in the 10.055.x network, router 1 should send that packet out the left interface. And the second route will tell router 1 that to reach anything in the 10.044 network, router 1 should use its right interface. Normally, the interfaces of the router would be slightly more technical, something like FA01 or GIG02 or ETH0 or ETH3. But to keep things simple, in this presentation, we're just going to use left and right to indicate the left interface or the right interface of the router. So that is a basic rundown of routers, and specifically the routing table. But the routing table is actually a very important concept in networking. In fact, a large part of a network engineer's job is to ensure that every router has the proper routes in its routing table in order to move packets through a network. Therefore, we're going to spend a bit more time digging into the concept of a routing table and discussing the different methods that routes are learned. There are three ways that routes can be populated in a routing table. The first method is what's known as directly connected. A directly connected route exists for every network that a router is directly attached to. In the
conectado, a rede está conectada ao
case of
roteador.
R1 is directly connected to two different networks, and therefore will have two different directly connected routes in its routing table.
Sim, tá.
The first one, telling R1 that the 10.055 network exists out the left interface, and the second one telling R1 that the 10044 network exists out the right interface. Now, if this is familiar to you, it's because it's the exact same thing we had a moment ago when we looked at R1's routing table, except this is a more formal way of displaying a route. Now let's add another network and another router to our topology. Here we have R2 in between the 10066 network and the 10055 network. Each router is going to maintain its own routing table, which means router 2 has its own routing table that is independent from router 1's. In each case, the routing table is a map of every network that router knows about. Just like before with R1, in order to attach R1 to the 10044 and the 10055 network, we had to configure an IP address in each of those networks. The same thing will apply with R2. For R2 to be attached to the 10055 network, we're going to have to plug R2 in and then configure an IP address in this network. In this case, we've configured the IP address 10055.2. This created a directly connected route in R2's routing table, telling R2 that the existence of the 10055 network exists out R2's right interface. In the same way, as soon as we configure this IP address on R2's left interface, this adds a new directly connected route to R2's routing table, telling R2 that the 10066 network exists out R2's left interface. Each of these routers will now use their own routing table to move packets through this topology. For example, if this packet shows up from host C with a destination IP address of 10055.8, that's host B's IP address, R2 will take a look at its routing table to determine that the 10055 network exists out the right interface and will forward that packet along. But what happens if host C now sends this packet? Well, this packet has a destination IP address of 10044.9. That's host A's IP address. When router 2 takes a look at its routing table, it's not going to find an entry for the 10044 network. At this point, router 2 does not know how to get to the 10044 network, which unfortunately means router 2 is simply going to drop that packet. When a router receives a packet with a destination IP address it doesn't know how to get to, the packet is going to be dropped. Remember, from the perspective of each router, the routing table is a map of every network that exists. And
O routing table, ou seja, essa tabela é tudo que existe. Se não tiver ali, ele dropa, tá?
At this point in time, router 2 does not know that the 10044 network exists. And since R2 is not directly attached to the 10044 network, it's not going to have a directly connected route in order to get to the 10044 network. But lucky for us, there are still two other methods that exist for how a routing table can be populated with routes. The second method to populate a routing table is what's known as a static route. A static route exists anytime an administrator manually provides instructions to a router about the location of a
Ali tu vai colocar as redes, é isso?
particular network. For example, I can log into router 2 and configure it with a static route, telling router 2 that anytime it wants to reach the 10044 network, it should send that packet to the 10055.1 IP address, which is router 1's IP address. Now, if router 2 receives
mas
this
vai dar
packet
errado.
from host C, it'll take a look at the destination IP address, find a match in its routing table.
Não. Caralho, que foda. Tu bota a rede da onde que tu quer mandar. A rede não, tu manda o IP do computador e tu coloca a rede. Ele vai na rede, opa, o IP é daqui, então toma. É
And
isso?
forward that packet along to the next router in the path, in this case R1.
Que foda.
R1 will then take a look at its routing table and determine that this packet should be sent out the right interface where it'll arrive on host A. So that's an example of a static route. But what happens if host A responds? This response is going to have a destination
Não
IP
tem como,
address
tem que
of
botar o static rule ali.
10.066.7, which is host C's IP address.
10.066.x
And when R1
e
receives this
botar
response, it's
a
going to take a
rede,
look at
que
its
é
routing table, and at the moment, router 1
10.066.2.
does not know how to deliver this packet. So normally, router 1 would just drop
Vai
this
dropar.
packet.
Aham.
But just like we use a static route to tell R2 about the 10044 network, we can also use a static route to tell R1 about the 10066 network. This static route would tell R1 that the 10066 network can be reached by going to the 10055.2 IP address, which is router 2's IP address. With this static route, router 1 now has instructions on what to do with that packet, which is to send it to R2. R2 will then take a look at its routing table to determine that the 10066 network is out the left interface, where it'll deliver the packet to host C. So notice we were able to use static routes to tell both of these routers about the networks that they didn't know about because they weren't directly attached to them.
E o terceiro?
The last way that a routing table can be populated is what's known as dynamic routes. A dynamic route is very similar to a static route, except instead of an administrator telling the router how to get to a particular network, a dynamic route is the routers automatically talking to each other and sharing it. A dynamic route is very similar to a static route, except instead of an administrator telling the router how to get to a particular network, a dynamic route is the routers automatically talking to each other and sharing information that they know in order to tell each other how to get to the networks that they can get to. For example, if we got rid of these static routes and instead told R1 and R2 to do dynamic routing amongst each other, R1 would share with R2 that R1 knows about the 10055 and the 10044 network. R2 would say, oh, I already know about the 10055 network, but I don't know about the 10044 network. Anything R2 gets destined to the 10044 network, it's just going to send to R1. In the same way, R2 will tell R1 that it knows about the 10066 and 10055 networks, and R1 will learn that anything destined to the 10066 network should simply be sent to R2. Now notice that the content of the actual dynamic route is identical to what it was with the static route. The only difference is how it was learned. If an administrator logged into the router and manually told the router how to get to a particular network, that is a static route. And if the routers automatically talked to each other and told each other of the networks that they know about, that is a dynamic route. Now the exact method that the routers will use to talk to each other to exchange these dynamic routes is governed by what's known as different dynamic routing protocols. There's a
Vou botar aqui. Mapear a rota manualmente de alguma de algum roteador de algum
A bunch of them that exist. The most common ones are right here. Each of these are simply different ways and different communication protocols that the routers will use to share routes with one another. Each of these differ insofar as how often networks are shared with one another, how they discover each other's presence, what sort of information is included with each route, and how much control you have over the routes that are received or sent. The inner workings of each of these is pretty fascinating and a large part of the network engineering career field, but unfortunately, the details of how each of these work is outside the scope of this particular module. The main takeaway of this lesson is simply that dynamic routing protocols are what are used between the routers. Hello, welcome to part 2 of lesson 5, where we will continue our discussion of routers. This is another lesson from my new course on networking fundamentals, which will teach you everything you need to understand how data flows through the internet. In this lesson, we'll continue right where we left off from the last video. In part 1 of this lesson, we used this topology to illustrate that routers have an IP address and a MAC address in each network that they are connected to. We also
Pessoal, deixa eu só botar aqui o ventilador que tá fora. Você vai pegar no vídeo, vai? Ah, só um pé do ventilador. Bora.
also learned that routers maintain routing tables, which is a map of every network that each router knows about, and that routes in that routing table can be populated in one of these 3 ways. We showed you all this by showing you router 1 and router 2's routing tables, and showed you how each router populates its routing table using one of these 3 methods. Now all of this was covered in great detail in part 1 of this video. If you haven't seen that video yet, go ahead and pause this video. Routers have routing tables, but routers also have ARP tables. ARP, if you recall, is a mapping of a layer 3 address like an IP address to a layer 2 address like a MAC address. Now we discussed ARP in lesson 3 of this series. In that lesson, I told you that everything with an IP address has an ARP table. Well, just like we just mentioned, routers also have IP addresses. Therefore, they also have ARP tables. And in each case, the router's ARP tables are going to maintain a mapping of IP addresses to MAC addresses of all the nodes in directly connected networks. Take a look at R1's ARP table right here. Notice in the 1044 network there is only one other node other than the router. And router 1 is going to have an ARP entry correlating to the IP address and MAC of host A. For this network, there are two other nodes in that network other than router 1. And router 1 is going to have an ARP entry for each of them. This one belonging to host B, and this one belonging to router 2. And router 2 is the same way.
Okay,
There's only
address resolution resolution ARP address resolution protocol, né?
one other node in this network, that's host C, and there's the ARP mapping for host C. And then in this network over here, there are two other nodes other than R2, and you have a mapping for each of them in router 2's ARP table. Now the thing about ARP tables is that unlike routing tables, ARP tables actually start out empty. A mapping for each of them in router 2's ARP table. Now the thing about ARP tables is that unlike routing tables, ARP tables actually start out empty. They will get populated dynamically as needed as traffic is flowing through this network. That's different from the routing table. The routing table has to be populated ahead of time. Recall that if a router receives a packet that it doesn't know how to deliver, the router is just going to drop that packet. But with ARP, if the router doesn't have an ARP entry it needs, it can simply do the address resolution process to figure out what it needs. We're going to show you how router 1 and router 2 use their routing tables and ARP tables in order to get a packet all the way from host A through both of these routers to host C. It's going to start with host A having some data it needs to send to host C. Host A knows the IP address it's trying to speak to, so it's able to construct a layer 3 header that's going to include a source IP address of host A and a destination IP address of host C. Now we discussed some reasons of why host A might already know the IP address it's trying to speak to. We reviewed that back in lesson 3. Feel free to check that out if you want a refresher. Either way, host A can look at the destination IP address and compare that to its own IP address to determine that what it's trying to speak to is on a foreign network, which means this packet must be sent to host A's default gateway, which in this case is R1. The issue is if this is the first packet that host A has sent, host A doesn't know router 1's MAC address and therefore cannot construct the necessary layer 2 header, which would take this packet from host A's NIC to router 1's NIC. So, before host A can send the packet, host A is going to have to perform ARP. So host A is going to send an ARP request for the IP address of R1, 10.044.1. That ARP request is going to ask for the MAC address for whoever owns the IP 10.044.1. Notice in the ARP request, host A is going to include its own IP to MAC address mapping. This ARP request will be sent across the wire, where it'll be received by router 1, and when router 1 receives the ARP request, router 1 will be able to learn the ARP mapping of the sender of the ARP request. Recall that the sender included the ARP mapping of host A, and there's nothing preventing router 1 from simply adding that ARP entry to its ARP table upon receiving the ARP request. Now router 1 needs to generate a response. That response will include the ARP mapping that host A was trying to resolve. When that ARP response gets back to host A will populate its ARP entry with the MAC address of its default gateway, and now host A has everything it needs to properly construct the layer 2 header, which will get this packet from host A to the router. Host A can now send all of this to the router. When the router receives this packet, the first thing the router is going to do is discard the layer 2 header. Remember, that header only existed to take that packet from this MAC address to this MAC address. It did so successfully, so we can discard that layer 2 header. Now router 1 will look at the destination IP address in its routing table. It's going to try and find a match to determine where to send this packet next. It'll see that there's a match right here, which will tell router 1 that the next hop for this particular packet is the IP address 10.0.552, which is router 2's IP address. Now, router 1 needs to construct a layer 2 header, which will take this packet from this MAC address to this MAC address. The problem is at this point, router 1 does not have an ARP entry for the IP address
Vai
10055.2.
gerar essa pergunta e resposta, né? Aí ele vai falar, opa, eu sou o E2, E2, E2. Vai
Therefore,
mandar pra ele vai registrar ali no R1 a RP e vai mandar.
router 1 cannot construct a layer 2 header as necessary, which means router 1 is going to have to perform the address resolution protocol. Router 1 will send an ARP request for the IP address 10.0.55.2. Just like before, the ARP request includes the sender's ARP mapping. This is going to allow R2 to learn the ARP mapping of the sender of that ARP request. Upon receiving the ARP request, R2 will learn that something with the IP address 10.0.55.1 has the MAC address EEE3. Now, R2 will generate an ARP response. This ARP response is the ARP mapping that router 1 was trying to discover. When router 1 receives this ARP response, router 1 will be able to complete its ARP entry and therefore able to create a layer 2 header which will get the packet through to the next hop. Now, this packet can be sent from this NIC to this NIC. Once it gets there, router 2 is going to receive the packet and discard the layer 2 header. Again, that header only existed to go from here to here. Then, router 2 will look at the destination IP address in the routing table to try and determine what to do with that packet next. It'll find a match right here, indicating that this packet needs to be delivered out the left interface. Since router 2 is now delivering this packet through a directly connected route, it knows that this is actually the final hop for this particular packet, because the destination exists in a directly connected network. So router 2 will need to construct a layer 2 header which will take this packet from router 2's NIC to host C's NIC. But just like before, router 2 currently does not know host C's MAC address and therefore cannot create the layer 2 header. Router 2 is going to have to send an ARP request to resolve the layer 2 address for host C. This will follow the same process we've already outlined. Host C will learn the MAC address mapping for router 2 by receiving the ARP request from router 2. This will be useful for the return traffic back to host A. Then host C will generate an ARP response. This ARP response is going to include the ARP mapping that router 2 was trying to resolve. Once router 2 receives the ARP response, it'll populate its ARP table with the appropriate MAC address, and then it can finally create the appropriate layer 2 header to get the packet to host C. When host C receives this packet, it's going to discard the layer 2 header. Again, this header's purpose was simply to take the packet from this NIC to that NIC. Then host C is going to discard the layer 3 header. The purpose of that header was simply to take the data from this IP address to this IP address, and finally host C will process the data. And that is every single step that needs to happen in order to get data from host A to host C. Next, I'm going to show you what needs to happen in order to get a response from host C back to host A. But you'll notice the way back will go much quicker because all of the necessary ARP entries have already been populated. Just like before, it's going to start with host C having some data to go to host A. Now these routers, to get this packet instantly create host A, would repeat for Hello, welcome to another video from Module 1 of our Networking Fundamentals series. This module will teach you everything you need to understand how data flows through a network. This is part 3 of our lesson on routers, and in this video we will tie together some of the concepts we discussed back in lesson 1 with the concepts we just illustrated in the last few videos. In the last video, we showed you everything that happens to get a packet from host C to host A, and then back. We showed you all the steps required for these two routers to hand data to one another. These routers happen to be deployed in a line, or linearly. But back in lesson 1, I showed you this topology and told you that routers are deployed in a hierarchy. And in this lesson, I want to show you why. Routers in a hierarchy allow topologies to scale much easier and provide more consistent connectivity for the users in the networks. So let me explain both of those points. Let's say the Tokyo network decides to expand and add 2 more networks, the accounting network and the help desk network. In each case, a router is stood up to handle the traffic for each of those networks, and that router is simply connected once into some sort of aggregation router, and instantly both of these networks now have connectivity into the rest of the topology of the Acme network. Hopefully this can show you that a network design where routers are deployed in a hierarchy is much easier to scale. To explain this second part, however, we're going to reconfigure these routers so that they are not deployed in a hierarchy and are instead deployed in a line, linearly. Notice now, if the sales team wants to speak to someone in the marketing team, they only have to cross 3 routers to get there. But if the sales team now needs to speak to someone on the help desk, they now need to cross 5 routers to get there. And this same effect actually happens in the reverse direction for traffic going to the internet. Notice the engineering team to speak to the internet only needs to cross 3 routers. But the accounting team, one of the new networks that we just added, needs to speak through 5 routers to get to the internet. So you can see that if you deploy your routers in a line like this, you don't have very consistent connectivity. The sales team is going to have a faster time getting to the internet than your help desk. Plus, if some sort of failure event happens at the marketing router, that happens to cut off access to the rest of the network for all the teams deployed after the marketing network. You don't have those problems if your routers are deployed in a hierarchy. If something were to occur to the marketing router here, no matter what, the accounting network and the help desk network is unaffected by that. Plus, for the sales team to speak to engineering, we have to cross 3 routers, or for the sales team to speak to the help desk, you still have to cross only 3 routers. And of course, in all cases, for any of these teams to speak to the internet, they just have to cross 2 routers. This makes for a much more consistent connectivity experience for the users in your network. So those are some reasons why you want to deploy routers in a hierarchy, because it allows for your topology to scale much easier and creates a more consistent connectivity experience for your users. Of course, routers being deployed in a hierarchy doesn't invalidate the illustration we did in the last video of packets flowing through linear routers. Because even if the routers are deployed in a hierarchy, the path between hosts flow through routers as if those routers were indeed linear. So our illustration from the last video, which showed you how routers pass data to one another, still absolutely applies. Host C from our previous example could absolutely be some host in the sales team of New York. And host A from our last video could absolutely be a host in the marketing team in Tokyo. All the routers in between form a linear path which data would flow through to travel between these 2 hosts. So these are 2 reasons why physically routers are typically deployed in hierarchical topologies. But there is still another reason which I'd like to unpack next. And that reason is that routers in a hierarchy allows for what's known as route summarization. To explain route summarization, let's focus on router 5 for a moment, and let's take a look at router 5's routing table. In the last few videos, we discussed that every router has a routing table, and that routing table is a map of every network that exists. In this topology, we have 6 networks, and router 5 is going to need a route for each one of them. There'll be 3 networks to account for the 3 teams in Tokyo, pointing to router 6, router 7, and router 8, respectively, and 3 more networks accounting for the teams in New York, each pointing to router 4. Now I want to quickly pause and talk about this /24 real quick. To explain it fully, we'd have to dive into the world of subnetting, which we're not going to do in this module. But I do want to give you a quick glimpse into that world to explain what the /24 means. When we say /24, we mean that these routes are going to match on the first 3 octets of a destination IP address. This /24 refers to the bits in the IP address. Remember back in lesson 1, I told you that an IP address is simply 32 bits, which we break up into chunks of 8 or 4 different octets, and we represent each of those octets as a decimal number. That's all an IP address is. And when we say /24, what we are saying is we're going to match on only the first octet, which is the New York office.
É só criar um table route e colocar lá uma técnica que usa e reduzir o tamanho de complexidade, agrupando várias rotas. Ah, tá. É isso mesmo. a sumarização de roteadores.
Hello, welcome to another video from Module 1 of our Networking Fundamentals series. This module will teach you everything you need to understand how data flows through a network. This is Lesson 6, where we will unpack the idea of networking protocols and give you a brief description of a few important protocols you should know about. Now, we've actually used the term protocols a few times in this course without giving you a formal definition, and I'd like to start there. A protocol is simply a set of rules and messages that form an internet standard. For example, we've discussed the Address Resolution Protocol, or ARP. In this course, we've told you that ARP resolves IP to MAC mappings. This allows two hosts to discover each other's MAC address if all they know is their IP address. They do this by sending out an ARP request, and the receiving host sends an ARP response. The key, though, is someone had to determine what an ARP request looked like, what question was asked in the ARP request, or what information was included in the ARP request, or what to add as the destination MAC address in the ARP request. In the same way, something had to decide what an ARP response looked like. Well, in the case of ARP, that set of rules is defined by RFC 826. You can actually look up RFC 826 to see the specific rules for what actually makes an ARP conversation. The RFC are the engineering implementation guidelines for how to do ARP. This RFC has all of the rules that govern what an ARP request is and what an ARP response is. And the fact that these rules are published as an internet standard allows ARP to be implemented by many different vendors. That's what will allow a HP server to speak to a Apple MacBook, or a Dell laptop to speak to a Samsung phone. All these different vendors are simply following the public open internet standard for ARP, and that's what allows them all to speak the same language when they're doing ARP with one another. That is the definition of a protocol. Again, it's simply a set of rules and messages which create an internet standard. Just like ARP is an important internet protocol that you should know about, there's a few other internet protocols that I'd like to introduce to you, starting with File Transfer Protocol, or FTP. FTP allows a client and a server to send and receive files from each other. The FTP conversation is made up of messages that look like this. The client would send the RETR command, which stands for retrieve, and ask for a particular file. and this would prompt the server to respond with that file. There's also the SMTP protocol, which stands for Simple Mail Transfer Protocol. This is the protocol that email servers will use to exchange emails. That conversation looks like this. The client will send the hello command to an SMTP server. The SMTP server will then respond with a response code of 250, and now the client and the server can exchange emails with one another. Hello and 250 are simply some of the messages in the SMTP standard. There's also HTTP, which stands for Hypertext Transfer Protocol. This is the protocol you're using anytime you're communicating with a web server. Web servers host many web sites written in HTML, which stands for Hypertext Markup Language, and those HTML pages are exchanged using HTTP. When you browse to site.com, your client, your web browser, is sending a GET request to the web server, and the web server will respond with a 200 OK message and then provide the website you're asking for. There's also the SSL and TLS protocols, which allow a client and a server to build a secure tunnel between themselves, and then they can do that HTTP conversation within that tunnel. That process is what's known as HTTPS. That is in fact what HTTPS stands for. It's an HTTP conversation secured within an SSL or TLS tunnel. That's what allows you to browse the web securely. So that's a quick rundown of some of the important protocols that exist on the internet or TLS tunnel. That's what allows you to browse the web securely. So that's a quick rundown of some of the important protocols that exist on the internet. There are thousands of protocols out there, and all of them contribute to some sort of functionality in the internet ecosystem. And there's two more rather important ones that I want to talk about, but first I want to focus on the host for a minute. In lesson 1, we told you that a host is anything that sends or receives traffic, and that hosts are typically divided as clients or servers. But we also said that a server is really nothing more than a computer that knows how to respond to specific requests. meaning each of these servers are really just computers that have FTP software installed, or SMTP software installed, or HTTP or SSL software installed. Which means these clients and servers all follow the same rules of host-to-host communication that we unpacked in Lesson 3. And one of the key elements of that is for a host to speak to another host, it must know the other host's IP address. Now this will work for this client to speak to the FTP server, because we can see the IP address right here. But how does it work for this client to speak to the SMTP server or the web server? If I asked you for your favorite websites, you would probably give me the domain names of your favorite websites. Or if I asked you for your email address, you would give me something that looks like this. You wouldn't give me an IP address. Lucky for us, there is a DNS server will provide an IP address, and this will see DNS is actually a pretty important protocol in the internet ecosystem. This is going to serve as the host identity. The host has address. These four things must be configured. Discover message to discover the DHCP server, and then the DHCP server will provide these and a DNS server for any client. This is actually what happens every time you connect to a new Wi-Fi network. Your host will send a DHCP discover message to discover the DHCP server, and then well, what's occurring behind the scenes is yet another important internet protocol. And that internet protocol is known as DHCP, the Dynamic Host Configuration Protocol. What DHCP does is it allows a DHCP server to provide an IP address, a mask, a default gateway, and a DNS server for any client. This is actually what happens every time you connect to a new Wi-Fi network. Your host will send a DHCP discover message to discover the DHCP server, and then the DHCP host needs in order to overall internet ecosystem. Either way, that wraps up this lesson. I hope you enjoyed this video. I want to thank you for watching, and I'll see you in the next one. Hey YouTube, I hope you enjoyed that free lesson.
Eu vou almoçar. Eu já tinha visto sobre esses protocolos, eu tenho que botar tudo em prática, cara. Tudo em prática mesmo pra aprender, né? Rapaziada, mas agora eu vou almoçar que eu tô com muita fome. Não tem jeito, sério mesmo. Bom, é isso, daqui a pouco estamos de volta aí. Bom, pessoal, eu ia parar, tá ligado? Não ia gravar a última sessão, mas vambora. Vambora. Vamos lá, vou botar aqui. Me dê 60 exercícios sobre network fundamentals. Com network fundamentals. 5 alternativas. E não deu gabarito. Vamos soltar aqui. Vambora. Ai. Vamos botando aqui. Acho que eu não vou precisar mais do caderno por hoje. Vou só ficar fazendo exercício pra massificar o conteúdo, né? Pra massificar o conteúdo. É letra B. 2. Vou botar no bloco de nota pra não enviar, mano. Deixar aqui. Captura o monitor mesmo, vamos embora. Letra B. 2. Qual dispositivo conecta a rede? Escolhe o melhor roteador. 3. Modelo OSI 7. Por enquanto tá de boa, né? Qual das alternativas representa a camada física do modelo OSI? Cabo de rede. Qual a função do protocolo TCP? B. O que é um identificador? Uma rede, letra B. 7. Qual a principal função de um switch? Conectar dispositivo a uma rede local e gerenciar o tráfego, né? 7 letra E, 8 letra. Qual protocolo é usado para tradução? DNS C9. Qual é a porta padrão do protocolo 80? D10. Qual o significado é Dynamic Host Configuration? B. Repetidor. 12. Que característica é um tipo de LAN? Conecta dispositivo em uma área limitada. Letra C. 13. Qual protocolo é IP rede? 14. Qual do seguinte IP é válido? B. O que é uma máscara de CV? É um número que determina o intervalo de um IP. B. O que é NAT? Eu não lembro. Ah, letra C. 17. Qual endereço não pode ser o IP de rede pública? Letra C, eu acho. Qual dos seguintes é usado para envio SMTP? SMTP, letra B. 19. O que é um domínio? É um nome simbólico que representa. Letra C. 20. O que significa VPN? Virtual Private Network. Letra D. 21. Qual tecnologia permite a comunicação sem fio? Wi-Fi. Qual é o Qual o principal benefício de IPv6? É mais endereços disponíveis. 21. Em rede, o que é latência? Eu acho que é... Não, é o tempo de memória, isso aí mesmo. O que é um firewall? Um sistema de segurança que controla o tráfego. Pô, só a letra C, mano? Que porra é essa? 24, 23, 25. Que é o endereço MAC? É o endereço de IP dinâmico, é um identificador único de interface de rede. Cara, é o endereço físico, né? Vamos botar assim. Qual das opções representa a camada do modelo? Qual das opções representa a camada de transporte? C. Mano, é só a letra C, que porra é essa? O que é largura de banda? Largura de banda, cara, é... Mano, só a letra C, velho. Que porra é essa? Eu acho que é a quantidade de dados máxima que pode ser transferida. O que define a topologia? Letra D. 29. O que é spoofing? C. Qual das alternativas é um tipo de cabo par trançado? Ixi. Não lembro, velho. Vou botar que é HDMI, não D4, acho. Qual protocolo é usado para acessar remotamente um dispositivo de segurança? Acho que é SSH. O que é ARP? É o que traduz, é. C. Em rede Wi-Fi, qual... Cara, eu acho que é a letra B. Qual é a porta padrão do protocolo HTTPD? 35. Qual alternativa representa um protocolo de transferência de dados? FTP. 36. Qual ferramenta é usada para testar a conectividade entre dois dispositivos? Ping. 37. Qual dispositivo opera principalmente na camada 2? Camada 2 é switch, né? Switch, né? 38. O que é um SSD? É um endereço IP interno. É o nome? Não. Letra B. 39. O que significa QoS? A qualidade. Security. Letra D. 40. O que caracteriza um ataque DDoS? D. 41. Qual o comando exibe informações de configuração de IP? ipconfig, mano. 42. Qual a principal SNMP? Eu não lembro. Vou botar aqui A. Qual a camada do modelo lateral de criptografia de dados? Seção. Não, apresentação. 44. O que é um DMZ? Delimiter Zone. B. Qual das opções representa uma rede que cobre grandes áreas geográficas? Acho que é um WAN. O WAN. 46. O que caracteriza um protocolo de estado de conexão? Garante C. 47. O que significa o protocolo ICM? Vou de B, mano. Não sei. Qual comando exibe o caminho de um pacote? Tracert, acho. Não sei. Qual o propósito de um servidor proxy? Letra C. 50. Qual das alternativas é uma técnica de segurança de rede? Acho que é criptografia, não sei. O que faz um protocolo HTTPS diferente? Ele criptografia. B. 52. O que é um subnetting? Dividir. C. 53. Qual protocolo permite a obtenção automática de um endereço IP? DHCP. 54. Qual o padrão de um cabo Ethernet mais... Porra, não vou saber, eu acho que é D. Qual dos seguintes não é um tipo de topologia? Estrela, barramento, anel... Acho que círculo não é. Malha eu não lembro qual é o tipo de topologia, mas eu sei que é. O que é TLL? Tempo de vida, eu acho. Tempo de vida. O que é uma VLAN? É uma rede local separada sem... que separa lógica, sem separação física. D. 58. Qual comando exibe conexões ativas e portas? Vou botar net, não sei. 59. Qual serviço de rede? Qual serviço de rede traz dos domínios? DNS. 60. Qual número representa a máscara? 8 vezes 3, 24, letra A. 55, o que eu errei foi 55, 47, 38. Deixa eu anotar o gabarito, né, animal? 5D, 47 A, 38 C, 34 E, 33 E, 30 C, 17 B, 5 D. Vamos lá. Vamos comer pelo 5. Qual é a função do protocolo TCP? Não, tem que estar erradíssimo. Permitir, não. Garantir entrega. Não faz sentido isso aqui, mas tá bom. D foi. Agora vamos para 17. Falando que é B? Acho que é, né? Não sei. Vamos para 30, né? 30, 33, 34, 38. 30. UTP, tá. 33, letra E. 34, letra E. Qual é a porta padrão? 443 do HTTPS? Caralho, não sabia disso aqui não. 38, letra C. Ah, verdade, é o nome de... Não, eu viajei disso aqui. 47A, né? Internet Control Message Protocol. Tá, e 55D, né? Deu, mas marquei D, né? Tá bom. Rapaziada, eu vou ter que fazer um negocinho aqui. Já eu volto, rapidinho. Amanhã eu vou vir com o tema de programação, tá? Só pra já deixar avisado. Não sei o que eu vou estudar em Java, mas alguma coisa eu vou ter que estudar, mano. Não tem jeito. Opa. 16. 1, 2, 3, 4. Sub-rede vai modificar aqui. Dois, a letra A. Quantos hosts válidos podem existir numa... Com a sub-rede o quê? É uma do tipo classe C, né? A gente sabe que é classe C. E 192 para dar 192 tem que ser os 3 primeiros, né? Não, tem que ser 2 primeiros. Então tem que 16, tem que ser barra 18, né? Dezoito bits uns, né? Eu vou botar... 254, né? Quatro recebendo. Vamos ver aqui o 5. A gente sabe que 192.168.1.130 barra 26. O que vai mudar? Nove dois, né? Vai pular de 64 a 64, né? Mais 4, 196. Mais 60, 246, né? Mano, 190 mais 60. 10, 190 mais 60. 105, 250. 250, 26 vai dar? Mas não pode ser 256. Então aqui vai ser 1 e 0. Aí aqui eu boto 192.168.0.254. E aí eu venho ponto 1 64, né? Vou botar aqui 192.168.1.128. Cento e 20 até 91. Então aqui vai ser de 192.168.1.129 até 192.168.1.190. Letra B. Ué. A 5 B 3. Letra E, vamos ver. Ah, acertei sim. Rapaziada, bom, é isso. Vou finalizando por aqui. E obrigado. Só tenho a agradecer.